Okay, today we will make final remarks of thermodynamics first, starting, and we will start fluids, Archimedes principle, uh, hydrostatic, Bernoulli. You will understand why the planes can fly, why the fishes can go deep in the water, or why they can go up. What else? Bernoulli, bam, bam, bam. Of course, how to transmit force through fluids. That's very important. Another issue which in the past, I will remember or before, we will start with the final remarks of thermodynamics. No? Remember thermodynamics? And I will start with the entropy issue. Entropy, because there was something I remember from the last class. Let me see if this marker is entropy. This is all the light we have. Remember that the entropy only flows as when the heat flows, no? Or when the disorder of a system changes. We saw before, for example, that if I have a tank here, full of air here, and I move this barrier, the air spontaneously will fill the other half. And this is an increase of entropy because the entropy measures the information I have about the molecules inside. Before, I have more information because I knew, well, it actually is related to the uncertainty principle we see in quantum mechanics later. We knew with more accuracy the location of the particles. But once you remove the barrier, you know less the location. The interesting issue of the entropy is that its formulation as a natural logarithm of the number of possible states consistent with the macrostate was done after all these guys did the formulation empirically. So imagine those guys in the past, they did this empirically, and then subsequently some guys with the mathematics did the right formulation. I want to close the entropy part because we did calculations of entropy. You remember, we defined the change of entropy as the integral heat divided temperature. We define. So when the heat flows from one body to the other, if the body receives heat, it receives entropy. If the body releases heat, the entropy decreases. But there is no violation of the second law of thermodynamics because the total entropy increases. The entropy which decreases plus the entropy which increases at the end is larger than zero. But then we evaluated the Carnot cycle. You remember the Carnot cycle in that case? And we evaluated the ratio of some heats. The reason for that ratio is the following. If we have a thermal reservoir or a source at constant temperature, let's assume that the temperature of this source doesn't change, no matter how much heat it emits. Then the change of entropy, this could be a source like this, could be the atmosphere, it could be an iron heated permanently receiving input from the electricity input, and you just let at a constant temperature, or for example, the ocean. We talk about perfect reservoirs, no? Imagine a perfect reservoir. So the change of entropy in this case is the heat flowing divided the temperature, because the temperature is constant. When you integrate this, it's only heat. With this quantity constant, you can remove from the integral. So this is a way to calculate. So in the case of Carnot, in the Carnot cycle, because I want to remark that part before, you have a source, you have a sink, and both of them are perfect, high temperature, low temperature, and there is an engine here emitting a work. This is QH, QC. Let's call C for hot. Then, of course, the change of entropy of the source is QH divided T. The change of entropy of the sink is QC divided TC, TH, like this. So in other words, since they are perfect source and perfect sink, And what happens if I sum both entropies? The total sum, because it's an ideal cycle, the total entropy change is zero. It's zero. So at the end, when you see, this is negative, no, this is negative because it emits heat. No, the flow heat is negative, and this is positive. So at the end, let's put absolute values here. There. Then when I sum both, there's H equals zero, you will realize, it's not difficult to realize that that's why you have QH, QC equal to TH, TC, which is what they use in the Carnot cycle for analyzing the efficiency. Remember, the efficiency of an engine is the work divided by the what you invest. What you invest is this heat from the high temperature. And what you release, effectively, what you produce is work. What the work is the difference between QH minus QC. So at the end is 1 minus QC, QH, and at the end is 1 minus TC, TH, which is what we saw last time. With the refrigeration is the same, but in the opposite direction. And refrigeration, we don't use efficiency, we use coefficient of operation. Okay? I will send you some notes about that, but it remains for you as an exercise. In refrigeration, this principle applies also. The change of total entropy is zero, and the ratio of the heats then is equal to the ratio of temperatures. So you should be able to calculate the coefficient of operation, which is larger than 1. And why is larger than 1? Because what you invest in that case is work. You invest work, but at the end, there is a difference in heat here, no? So let's say you calculate first and let me know. So homework, calculate the coefficient of operation, which, remember, is larger than 1. Of course, it's like investing this relation. It's like putting in the opposite sense. No? But now the work is what you input, so it will be the denominator, and the numerator will be something else. So try to evaluate. Okay. So coming back to the closing remarks of thermodynamics. So if I ask you in an exam, for example, that I have a glass like this, and I put a very hot iron heated at 200 degrees, and water is at 20 degrees, and I ask you which one of these two guys increase the entropy in this process. This is a thermodynamic process because, of course, the heat will start to flow from where to where? From the iron to the water, exactly. So who lost entropy? This guy, right? The water win entropy because the water is receiving the heat. Remember that the heat flows from high temperature to low temperature, and at the end there will be an equilibrium condition. The tendency in nature is to be in equilibrium. We want to be in equilibrium always, permanently. If the processes spontaneously are always looking for equilibrium conditions, that's something you should know. So let's summarize something in details, the thermodynamic laws. We close this chapter and we start the new episode. No, we did this problem before. You remember we did in the last class this problem where we put an iron inside the water, and we calculated change of entropy. Actually, we calculated the change of entropy. Now, something I want to remark is the water. I want to ask you this question. Why we cannot use the water for thermometers? Why the water is a bad liquid for using it as a liquid for the thermometers? For the thermometers, we use mercury normally. When the mercury expands, when they tell you temperature, the mercury suffers dilation, And of course, people know what is the coefficient of dilation of the mercury, and they mark the lines. This temperature corresponds to this expansion, this temperature, like that. It's not that the liquid knows, it's that we know how it behaves, and we mark the lines. So what happened with the water? Why the water cannot be a good liquid for that? That's one reason. And there's one even more powerful than that. Think about it. What happened with the water between 0 to 4 degrees? Yeah. For example, if normally if I heat water, when water is boiling, the tendency to expand, no? Consistently. When water is, I decrease the temperature, the tendency is to contract. But between 4 to 0 start to expand again. So as a thermometer will be bad, no? And in addition, it gets frozen at 0, for example. Then, well, we can have water as liquid at 0 degrees, but there is a phase transition. I explained that before. If you extract enough heat, you can produce the first ice at 0 degrees at atmospheric temperature. If you increase the pressure, this can happen at different temperature because it depends on the pressure also. Remember, we are assuming here that the pressure is a constant, that we are atmospheric pressure. If I don't specify anything, you have to assume atmospheric pressure. So between 0 to 4, or between 4 to 0, the water expands. And the reason of this expansion is because when the water starts to organize in solids, the arrangement of the molecules, I don't know the details, H2, well, you know, H2O, no? H2 oxygens, then is such, the arrangement is such that they create some holes, some space. And that's why the water expands. And thanks God, the water expands. And what's the reason? If you believe in God, of course, water is the ideal liquid for life, not only because we need it, but also because of this behavior. Because the oceans in winter, when they become frozen, they only get frozen on the surface. The water expanding when become ice is lower density. Lower density has the tendency to go up. And then at the end, in an ocean, you have a water of a pond, only this part, the surface gets frozen. The part below is liquid, and still the fishes can live. Nemo, Dory, all these kind of guys, they can live below. But I mean, yeah, just remember the Disney word. But if the liquid for living would be different, is different. Imagine that the water behaves normal as an ordinary liquid. Of course, if we have a high density, when it gets frozen, then the first ice will form here on the bottom. And then layer by layer by layer, and it will become everything frozen because the heat, the water starts to lose heat from the surface. So it means it will create ice here and it will sink. Then we create more ice, sink, more ice, sink, more ice, sink, and until it create all the ocean, basically completely will become frozen. And the fishes cannot swim. They would not live life. At least not in the way how we know it, no? Then the fishes will have to be in hibernation, probably. I don't know. Imagining here the hypothetical case that the water behaves as an ordinary. But fortunately, it's not the case, and that's why when you walk on the water, there is a chance that the ice gets broken and you fall, because it's only the surface. And how big is that layer frozen? Well, it depends on how cold is the environment and how long it has been the process, no? For extracting heat. So let's summarize the thermodynamic laws here. Zero law is the one for the doctor. Thermal equilibrium, three bodies, A, B, C. If A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. And we apply that the whole time. We apply that for the thermometers and for other devices. Then zero law. First law, First law is what? Conservation of energy. It's an extension of the conservation of energy we saw. In differential form is the change in Q, which is heat, change in work. And I explain why I write the differential like this, because it's an exact differential. It depends on the trajectory of the process. It's not exact differential as the change of internal energy. The combination of work and internal energy sometimes create another thermodynamic property called enthalpy. We use that in the pistons, expansions, at constant pressure, and other processes. But normally, and sometimes in the thermodynamic tables, appear in terms of enthalpy and not internal energy. Then you calculate the heat directly in certain processes, not in all. So anyway, an infinite form is Q plus W equal change of internal energy. And the work, we take the symbol positive. It means if the system release work or produce work, it's losing energy, so it's negative work. If the system receive work, it's positive because it's receiving energy. This is the convention used by physicists. In some books, you will find minus because the engineering people is thinking in production and money. Then if the system release work, it's producing. Well, it's exactly the same, but you have to get used to both conventions and how to exchange both of them. The second law is what we talked just now, the entropy, the change of entropy. Total entropy of a system is larger or equal to zero, is equal to zero in the ideal processes, like the Carnot cycle. That's why we can calculate the ideal efficiency. Carnot is the ideal efficiency, either in refrigeration process or in engine processes, is because we assume that the total change of entropy is zero. So there is nothing more ideal than Carnot. But even Carnot is not 100% efficient. So it means that when you make an engine, don't expect to compare with 100. That's a bad comparison. It's not fair to compare like that. What you have to do is to compare with the Carnot efficiency under the two equivalent temperatures between the source and the sink. And then you will say, okay, I am not that bad. Let's say Carnot is 40% and my engine is 38. Come on. You cannot complain, no? You cannot say, no, it's bad because it is very far from 100. So that's something to consider. With COP is the same. COP has to be larger than 1 if it has to operate correctly. But what to say, you use the same principles as Carnot. And now the third law is something we explored the last third law, because of course for the third law we have to go more to the very low temperatures where quantum effects emerge. Recently, normally we expect quantum effects to appear in macroscopically or at low temperatures or so. But recently, some scientists, I shared the news with these guys in environmental science. It seems that some biological processes, even of our brains, obey some quantum principles, especially the communication, this kind of instantaneous correlation also between different neurons or whatever. It seems to operate. I always suspected that was true, but it seems that nobody had tested it effectively in a laboratory, and it seems that it has been tested for first time. So the third law says that at the absolute zero, and absolute zero means 0 kelvins. 0 kelvins. The absolute temperature is Kelvin, not Celsius. Celsius is what we use normally, but Kelvin is the absolute. So in other words, 0 Kelvin is how many Celsius? Minus 273, right? Okay. Then at 0 temperature, principally the entropy goes to 0. Why? Because at those temperatures, the entropy in the microcanonical example is K natural logarithm of omega, where omega is the number of possible microstate consisting of the microstate. What does it mean that? If you have imagine you have this room at a certain temperature, a certain pressure, certain volume, and other thermodynamic properties which you wish. then I can configure internally the air inside or any gas which inside this room can be configured in many, many possible ways, consistent with the same temperature, the same pressure, the same volume. And that number of configurations is this omega. But when the temperature goes to zero, there is only one possible configuration because everything becomes quiet. But later, when you see quantum mechanics, you will see how bizarre is the quantum harmonic oscillator, for example, where the zero energy has still some, the zero level has still some energy, basically. So quantum mechanics is very interesting issue to introduce here, at least the basic, and you will see how nice it is, especially now that we have quantum computers coming, quantum neural networks, quantum whatever. I mean, everything is quantum. So not yet the cars. But what I want to say is that the technology is pointing to the quantum world, and it's important to have some input about what is quantum mechanics at least. And actually, quantum mechanics has some inherence in thermodynamics also, but not in what we saw. I mean, in the limits we evaluated, thermodynamics is classical. The statistical mechanics will be classical, but there are certain well, fortunately, we don't have a longer class, so you will not be able to see statistical ensembles, which will be interesting, but this is just a general physics class. We cannot go so far. So you should feel happy at least with learning with this learning. So this closes the remarks of thermodynamics, and I will start this video here. I always think that the light here is a little bit weak in this classroom. Probably we should open the windows. Okay, I will stop it.